All right. So my project is on the breadth first search model, parallelizing a breadth first search model. Basically, I had done a project before. It was a kind of like a slide puzzle. Simply, you could look up online like a nine tile slide puzzle, and it would be numbers roughly arranging from one through eight with a missing tile. In this case, when we're writing it here, it would be a zero. And what you would do is you would then make a algorithm of sorts that would basically solve the puzzle on its own. I did this project back last year or so. Yeah, last year I did this project and I just wanted to see how it could work with parallelizing it. So first things first, one of the kind of main things that I have is my first project one. So this is my old code that I utilized before. There's a lot of different functions that were done with it. I'll mainly highlight the one that's going to be most important for this project. It's going to be right here, our UCS. So it's our uniform cost search. Now, with this project, the uniform cost search kept the same marking as the breadth first search model. Um, and roughly looking at it, I know there's a lot of code here in some aspects, but roughly what it was is that it was nodes that would hold the array, the vector of sorts, which was the nine tiles. And it would then go through a queuing system of sorts that would look through, making sure any possible state has existed. I'm checking through all the stuff, making sure it doesn't hit any like reoccurring ones. And we'll go through every single possibility. And what would happen is once it is complete, it will then kind of return back the situation. And with how this system worked is that it would show the whole pathway that it took. Now, also with this project, it utilized some A-star methods that we learned in the class, utilizing the missing tile system or the Euclidean distance heuristic. But mainly, we're going to focus on the UCS or the breadth first search type system to kind of compare it to our GPU. And then we can see later on that how fast it works is kind of doing those things. Okay. So simply what I did implementing wise, I'll kind of show first here is you can just simply do a G++ to the item. And then what you can do is a dot slash a dot out executable that is made. And right here is when you would make your solver. So you can make your solver. I'll do a very simple one. You would write in your first three numbers, your next three numbers, and then your next three numbers. That's what the slide would puzzle would look like. You would then choose your algorithm, and then that's how it would be formed. With this one, it was very quick, very simple and stuff like that. But with a lot of the other algorithms that are shown in my report, which we'll go over later, it will kind of show how long it does take for some of these items with this, okay? So this is kind of how I did my CPU based one. Now, what is a little bit different now is I wanted to try it in the GPU sense. So right over here, we have our main, our kernel, and kind of our support. Our support is mainly kind of the same things that we're utilizing in our assignments, utilizing the start times, the stop times, and the elapsed times. And that's roughly it. Mostly the main is kind of some new things that were added that I learned throughout the process of when I was implementing this. So the difference between the CPU model and the GPU model is that the CPU model that I was utilizing was keeping the idea of like nodes, having a whole tree system, and doing all that. GPUs don't have that sort of like functionality to visually see trees and working those things out. So a lot of things that I had to change and implement was actually making a full array and actually making every single slide puzzle into a vector system, which I kept, but these vector systems were kept in boxes all next to each other um, throughout this whole queue system. So right here at the beginning, I make the initial array from whatever's given. I have two specific cases. If you want to get the default board, it would just give the first board, or if you want to make your own, very similarly to how I did this project on the on the CPU side, and making sure I synchronize this stuff. And then what I did is I allocated the device variables here. So the reasoning for this is so that the queue could have as much space as possible when all of these uh, arrays or like puzzle states are saved. So we have enough space for them. So we did a max queue size of roughly around, I believe, if I scroll up really quick, 100,000, because there's roughly around like 300,000 possible cases for the puzzle states, roughly around 100,000 it should fit inside. And the puzzle size, which is the nine boxes, I put it to a state of nine and it's defined up top. So that's the reason why we have to, I basically made sure that there's enough space for that. And I did it for the next queue. Now, the thing for this, which I kind of understood as I worked on the project, was when we're adding nodes into this queue, we need to understand how to work the threads into it. So one of the things that we first need to do is deal with the queues one at a time, or basically every level in the BFS one at a time. And so what would happen is when we go into our kernel model, we'll see that the main focus is dealing with the first queue, having the threads go individually through all the specific nodes that are in that queue. And as the threads are doing that, in the kernel model, they will add items into the next queue. So they will add the next, if there's a neighbor that connects to it, they will add that system there, and it would constantly go into this next queue. This next queue would then be flipped up into the queue, and the kernel would then run again. So it would pop, so the whole system will pop out of the kernel, go into the main code again, grab the next queue, putting it into the queue, and then that next queue will then set up another set of threads, making sure everything's all good, and run again through all the systems going through and stuff like that. The queue size and the next queue size are there so that we roughly get an idea of how big the queue is over time. The reason for why it's managed was because when I was using CUDA malloc on its own, it was never really working, and I kind of researched some things around, and managing it kind of allows for it to roughly work in that way to understand it and kind of work with the values that are changing. I do first make this initial queue right here, and I add it to the queue because we need to start with our first item and work then through there, and then working out the whole tree, but in this sense, the whole neighboring systems to add into the queue. And then we'll roughly hop into here, which is where this pops into the kernel system. This isn't the exact kernel function, but this is the one that goes into the kernel CUDA file. And so we can go into here. It's a couple of lines here and there comparative to my other one. Roughly right here, we have our design where we have all of our queues, our next queues, and our sizes. So first right here, we add this specific item into our visited. So I'll roughly scroll up to the top. We added some things here as well. So we added a solved tile, making sure that when we're on a specific level, we actually understand that when we are have one that's solved, we don't have to go through all of the codes in general and take and roughly have some issues with that solved. Once we have it solved, we can keep it there and keep it saved so that it's roughly an idea that we don't have an issue later on of like, oh, it was solved and then changed. This kind of roughly has it so that it can work into be that way, and also so that it ignores all the other cases of issues and stuff. The visiteds are basically another area of space. So when you're working with the BFS model, you need to track which nodes you have visited. So utilizing it here was kind of the main aspect of what we needed to do instead of putting it into the main, because the main doesn't really care about that visited stuff. It's mainly more focused in when we're working in our kernel space and stuff like a lot of these functions are helper functions, which we'll go over later on in the code, but we'll kind of go back to our main point here. I roughly made the visited point, and then this is where the loop kind of goes. This is the loop that will roughly go constantly until we've reached that solve case, and it's right here that we do our kernel model, keeping our same nodes here and there. We make our block size and our grid based off of the amount of threads that we utilize. I roughly did 256 because I thought that would roughly be a good margin of number comparative to what our projects have done here and there when we're doing a 16 by 16 model, keeping those 256 threads. So I roughly wanted to keep it into that way. And a lot of the things that happens where you can see the allocation, uh, the deallocating situations. The reason being for this is, again, another issue that I was having through my project was trying to save the values specifically, and it wasn't really working. And I realized that, since it's always changing, and in order to do it, when we will see in our kernel value or in our kernel code, we need to change the value every time. And the way to work it in is utilizing that atomic add. But atomic add was not really working. I don't know why fully when I was just leaving a regular int variable. It needed to be a pointer of sorts, and that pointer made it to allow for it to work and kind of work it into those spaces and stuff like that. So the reason for this deallocation, if you see a lot of the time, is due to the fact that the integer value wasn't working on its own, and I had to roughly kind of switch things around with it. We then kind of end after the kernel, like I said, with setting up the queue to be whatever the next queue was. The next queue is now going to be where the queue is, and swapping the actual full queues so that it's now all set up so that we can then thread it again. All right. Now we go into our actual kernel model. We set it up as a global. We have our index specifically based off of how the system was, and we make sure that it's still in the exact queue. So we because some cases we don't utilize all our threads, we roughly have this idea so that we can just return out and not have to deal with it anymore, or roughly have issues and stuff like that. This is issues with warp divergence, but the thing is that later on we don't have to deal with those things. Then we have our current state, making sure that we now set it up. So we're going to set up our current state based off of how our queue, since our queue is based off of our index and stuff like that, how our kind of setups are. You can get the current state of where we're at and basically then create the neighbors for it. So I made a generate neighbors function. What it will do is it will track every single position, and you'll see it in kind of the code where it will track one up, one down, one left, one right, seeing if it's valid, and then adding it to this thing. It will count those numbers up, going through this for loop, and creating some sort of ID. Now, the reason for this ID is so that we can get an idea of of if this thing exists. A lot of the time when we're working with all this stuff, this is a bunch of arrays and stuff like that, array spaces, and we can't figure out a specific way. So I roughly kind of made up a random ID of sorts. Basically, I made an integer value where you would grab every single tile from the first all the way to the ninth, multiply it by 10, and then basically make it. You can kind of possibly see it throughout the code in some aspects, and I don't remember. I was using it to debug, so I don't remember if I fully added it in again, but that's kind of the rough idea of how it shows like every single individual number and kind of putting it in there. The last point right here is that I will check if it's visited. And if it hasn't been visited, then we'll add it to our visiting category because now this is technically a node that we have reached. So we'll add it to our visited code. We'll roughly give it an ID to being like, hey, we're now in this ID is given here. We will then also add it into our next queue because the reasoning being is that we visited it, so we know that it exists, but we're now going to add it into our next queue so that when we now flip it back, when we flip the next queue into the queue space, this is a node that we can now then go and find its neighbors and stuff like that. Another for loop to make sure it's all good, and then I roughly do an if case. Now we can go through a couple of these helper functions. The generate neighbors, as I said, the directions are done here. This is something that I also found off of someone else's idea of how they did it a lot faster than what I did. I did in my CPU based thing a little bit of an is side valid and checking every single specific case. But some models that I've seen actually utilize a way faster system. So I thought utilizing this could kind of help see how optimized the code can be. And then kind of working it into, again, doing a for loop, getting these new specific rows, finding if it's valid through right here, and then basically making it into some sort of way that it works out. So the neighbors function is a size of like 36 numbers where every single one would kind of get its own space. So the first nine would be for the first neighbor, the second nine, the third nine. If it went to all four, it would take up all the space. If it doesn't, we would then only set it up to that. And that's why we have our count variable so that we don't have to, so that we wouldn't have issues with reading in the rest of the neighbor space that was not utilized. And then our two functions here is goal state and is visited are two functions that are kind of focused on just determining if it's the correct space by utilizing this sort of formula that I made, and then also is visited by utilizing this idea of the ID that was made if it exists and all this stuff. You might see a lot of these things called device, and the reasoning behind we have to use device is because all these functions are called in the kernel function. And the reason being is that we can't go straight from writing from kernel to device. Sometimes in order to do that, we have to dictate having the device in front. This was another issue that I had, and it was some errors that I was getting on the code. So the reasoning being that a lot of these have device is because of that. Now, roughly to kind of work this in, you can uh, create the make file that was made. This make file is specifically for it. I haven't updated anything on it, so everything's perfectly fine. And you do dot slash slide puzzle. For the dot slash slide puzzle, it's just the default one. So we'll make it and simply be done with it. But for if we wanted to make something new, let's just do a very similar one to was made. You would add in every single number in one line, and in the main CUDA file, it takes care of all of the value spacing. And right there, it's made again, doing it all that. The one issue that was happening here is that for the CUDA model, it doesn't show the pathway. I was struggling to try and figure out what are the specific things behind it, how to figure it out, but it was kind of a little bit difficult to get the tracking working and stuff like that. But the goal reached does work with how this function is. I know it's really hard that you can't see it fully in this visual code, but just to kind of understand that it does check every single possibility and reaches those specific things. Now, there were some functions that I had made before. In my report, I made a bunch of different move sets. So ones I chose was 12, 16, and 18, roughly to get a rough number of those things. Um, One of the things that I'll say from my end was that the 12 to 18 roughly scaled in a lot of different numbers. The 12 moves took about 4 seconds, the 16 moves took about a minute, and the 18 moves took about 9 minutes. Now, these numbers can roughly change here and there due to the fact of how, having a bunch of things running on the computer and stuff like that, or things changing here and there. But roughly, marginally wise, that's roughly the number of how long it would take. Now, running it through the CUDA terminal, I'll just show you the 18 move one. The 18 move one took about 9 minutes when I was running it at first. And when you run it through the CUDA simulation with it parallelized, it roughly takes about 0.09 seconds, which is really, really impressive how much of a big change it can be. And another thing that I realized when working through this is that I tried an impossible case, which we had to do for our project. And the problem is that it took so long, roughly it took over an hour for it to even fully work. And I just kind of would give up and I wouldn't let my computer run because it would take so long. But this one is an impossible case from what I remember. And this gets done in roughly a second, a little bit more than a second. And this has ran through every single possibility and determines that it is not possible. You can see right here, it doesn't show that the goal was reached or anything like that. So what I think is very, very impressive is the fact of how parallelizing code can just really fully take over and kind of simplify the amount of time it takes for these functions. Um, that's kind of a rough demo of a lot of the different things. If you wanted to try working with the heuristic models uh, on the CPU side, you would roughly choose your number. So one would be uniform clusters, two would be for the misplaced tile, and three would be for the Euclidean distance. Um, but yeah, that's roughly if you wanted to test those time-wise. Roughly when I did my timers, I just utilized my phone timer because it was roughly a little bit wonky sometimes to utilize the thing through C++ because that function or that specific coding style was done during in C++. So I couldn't really figure out how to do the start timings based off of that. But for the CUDA model, I'm utilizing kind of what was done in the Bender system, and it roughly gives the numbers right there in that sort of space. So roughly that's a little bit of the demo. There's some little aspects that are lacking in some aspects, but you can roughly see where the goals were reached and all those specific things. But yeah, this is my project on how a BFS model can be parallelized and showing it in a specific project-based thing. For example, an AI slide puzzle solving system. Thank you so much.